you a picture of the Milky Way. The Milky Way is our home. It's our home galaxy. This is an artistic conception because we are inside the Milky Way. So we cannot see the Milky Way from above. It's just an artistic conception of the Milky Way. When we talk about stars, we talk about very large things. And to understand these very large things, I have to use some units of measure that we are not used to work with them every day. For example, the diameter of the Milky Way is something between 150,000 light years to 200,000 light years. It means that light leaving this side of the Milky Way would take around 200,000 years to reach the other side. Light is the fastest thing we have in the universe. So, the Milky Way is a very large object in the sky. Well, it contains around 4 billion stars, and the Sun is around 26,000 light years from the Milky Way center. It means that the light from the Sun, or the light of the center of the Milky Way, would take 26,000 years to reach us. Well, so when we talk about stars, we usually use to measure distance in light years. But another unit that we are using a lot in this presentation, or in astrophysics, is a unit called parsec. 1 parsec is around 3 light years. And 1 parsec is 3 times 10 to 16 meters. It's a lot, okay? So, we are starting to, I will use these units a lot in this presentation. Well, this is an artistic conception of the Milky Way, but here we have a picture of the Milky Way in the sky. We are inside the Milky Way, so this patch of light that we see here, we cannot see the Milky Way in our metropolitan zone, but if we go to a farm or to the countryside, a place where we don't have too much light polluting our skies, we would see something like that. A very large patch of sky covering all the sky above us, okay? That's interesting. The interesting here is, if you can see, there are a lot of dark patches on the Milky Way. These dark patches are clouds. There are clouds inside the Milky Way, okay? And inside those clouds we have dust and a lot of gases. These patches are so large that they block the light of the stars that are after them, okay? So these dark patches on the Milky Way are really there, and they are clouds inside the Milky Way, okay? Most of the stars, all of the stars in the Milky Way are formed inside those clouds that we are seeing there, okay? Well, this kind of cloud is called the giant molecular cloud. Well, these clouds are, the Milky Way is full of those clouds, okay? The size of these clouds varies from a few parsecs or some light years to hundreds of parsecs or hundreds of light years, okay? The mass inside those clouds sometimes are a little more than the mass of the Sun, and we have clouds that have 2 million times the mass of the Sun inside those clouds. Okay, most of these clouds are composed mostly by hydrogen gas, and there are other kinds of molecules inside. Carbon monoxide, ammonia, carbon sulfide, water. Water is one of the most abundant molecules in the universe, okay? So there are a lot of water inside those clouds. We have methane, and we have even some more complex molecules, like some people already detected amino acids in those clouds. So, what is the reason to study how the stars are formed? Why do we study it? One of the greatest questions we have in science today is to explain how life evolved in the universe, if there is life anywhere else in the universe, not only here on Earth, and to answer how life started, we have to understand the source of life. The source of life, of course, there would be no life here on Earth if we didn't have a sun, a star around, a star where the Earth revolves around. So, to understand the star and how a star is formed or how a star is born, we are trying to understand how the planets are formed and how this material appears, how the first organic molecules formed, and then to understand how life formed in the universe, how it evolved, and how did we came to where we are now here, and if there is life anywhere else in the universe. Okay, so studying the star formation is a key step to understanding the life in the universe. Well, these clouds are they have a very low temperature inside them. Temperatures ranging from 10 Kelvin to 20 Kelvin. It's like minus 250 Celsius degrees, okay? So it's very, very cold. And, as I told you before, these clouds are our stellar nurseries, where all the stars in the Milky Way are formed, or in any other galaxy too, okay? Well, so, here I have a picture, the same picture as before, but without the writings on the screen. I don't think you are. Well, this is the Orion constellation. If you can identify it, I don't think you. If you can identify it, but the Orion molecular cloud complex is a very large region in the sky where we have star formation happening right now. Okay, and here is the Orion constellation. Here is what we know as the Três Marias. Okay, these three stars here are the Três Marias. Okay? It's just well, this is another region of star formation in our galaxy. This region is called the Pillars of Creation. It's one of the most beautiful images that the Hubble Space Telescope took around the 90s, I guess. And here we can see these Pillars of Creation, a region of intense star formation. And you can see it on visible light. Visible light is what our eyes can see, okay? So, if we could see it on the telescope, we would see something like that, okay? But, when we start to use other kinds of lights to observe it, for example, infrared, this cloud seems to disappear, and look at the countless stars that appear over there. So our understanding of star formation started to improve when we start to observe the sky without using visible light. We start to use, for example, infrared. It started almost 40 years ago, in the 80s, 1980s, okay? So since the 80s, we started, before the Hubble Space Telescope, that was placed in orbit around 1992, if I'm not mistaken, there was already other space telescopes around the Earth. For example, one of the first space telescopes was called IRIS. IRIS was an infrared space telescope, and it was launched around the 80s, okay? So IRIS revolutionized our understanding of star formation, because with IRIS we start to look the sky with other kinds of light, not only visible light, okay? So infrared was very important to understand, to help us understanding how the stars are formed today, okay? Well, so how does it happen? So the star formation starts inside those giant molecular clouds. They are very large clouds, and for some reason, some of this, we cannot see it here, but inside the cloud there are regions with a density a little larger than the medium around it. Okay, so we have inside the cloud regions with more denser regions inside the cloud. Because of this higher density, for some reason, the cloud starts to fragment itself. So it starts fragmenting a lot of cores, and the cores start to collapse because of the gravity, their own gravity, okay? Well, so we say that the life of a star starts when this protostellar core starts to collapse. So we are counting time from 0 here, okay? We can see the size of these clouds, like 200 AU means like 1 parsec, okay? So initially, this is a small cloud around the size of 1 parsec, then it starts to collapse, okay? And while the star is collapsing, it's rotating. So this core is not still, it's rotating. And because of this rotation during the collapse, the material will not fall forming a sphere, okay? During the collapse, the rotation will make the material fall to the star, to the center, but instead of forming a sphere, it will start to form a disk. So here we have a central protostar. Around the protostar, we have a disk, and there are a lot of material still around this disk and the star, okay? From time 0 to the protostar over there, it takes around 100,000 years, okay? So a protostar usually also have those bipolar outflows. It's a jet. Okay, so during the star formation, some mechanisms inside the disk produce a jet that flows out of the star. Okay, well, so we have an envelope. We can see the star in visible light when it is in this phase of its life. Okay, so for we to see that, we have to use infrared light. So when we start using infrared, we start to see a lot of objects like that in the sky, okay? Well, after a while, the envelope that covers the star, it starts to dissipate. It starts to become more transparent. And when it starts to become more transparent, you start to see the star and the disk and this bipolar outflow invisible light. Okay? This object here is one object that we call a T-Tauri star. It's a T-Tauri star is we can say that it's a star in its teen years that has around the mass of the sun. Okay, it's a small star. The sun is a small star. Okay, and from 100,000 years to 3 million years, more or less, this disk falls into the star, and it will become more and more and less dense. And after a while, some material in the disk starts to coalesce and to start forming the planets around the stars. Okay, so from 3 million to 50 million years, we start to have planets forming around the protostar, around the star. Okay, and finally, after this disk disappears, we have a star. It's not the disk that tells if the object is a star or a protostar. It's what's happening inside the star. So we consider that an object became a star when most of its energy inside it are produced because of the fusion process, fusion of hydrogen into helium. Okay, so it's the fusion of hydrogen when it starts to happen inside the star that we say that the star has reached its adulthood. Well, here I have some images showing those jets. Okay, so these jets are called Herbig-Haro objects. We can see some jets here, a very small jet, and if we see a jet in the sky like that, we know that there is some star being formed inside here. So these jets indicate that we have a star being formed over here. Okay, and that is another Herbig-Haro object, and we can see here that the star is inside this dark area over there. Okay, well, that dark area is what we call, it's the disk that's around the protostar. Okay, we can see it here. This dark region here is that disk that revolves around the star. That kind of disk is called an accretion disk. Okay, and we have some other examples of accretion disk. Here we have something here. Here we can see it. We cannot see the star inside the accretion disk because it also has a lot of dust and a lot of gas. So it absorbs the light that comes from the star. Okay, so this dark patch here is what we call the accretion disk. And, well, we don't observe more just in infrared anymore. Okay, so since the Second World War, we start using radio telescopes too. And if we look, this image was taken by an observatory called ALMA. ALMA was a set of, I guess, 60 radio telescopes that are in the Atacama Desert, okay? And it's one of the most advanced observatories we have these days. So it's an image from ALMA showing an accretion disk, or here at the center we have a star being formed, and around it we are seeing the dark patches in the disk that might be regions where planets are being formed right now. So it's an image from 2014, and well, there are a lot of happening. There's a lot of things happening in the field of star formation these days because of ALMA. Okay, so this observatory is revolutionizing again our understanding of not only star formation but astronomy. Okay, and I guess that's it. Thank you.
Thank you, Gustavo. We have a couple of minutes to finish, and we're going to use these few minutes for questions as part of the round table. I'm going to ask only 2 questions here, and then I'm going to open up the questions for you so you can ask questions, okay? So my question, since the event is called English, the language of science, is how did you guys, the 3 of you, learn English? And how is English part of your professional life? Okay?
I guess I learned English, most of my English, playing video game. Yes. And well, I am also a fan of RPG games, so in the 90s, most of the books that we have about RPGs are in English. Well, and when I started to make my physics course at the CEFET-MG, it's very important that you know some English. So since the beginning of the course, the professors there start ask you to read papers, articles in English. Most of the books I had in the time were written in English too. So it was very mandatory to learn English if you want to keep on the course. Okay. And well, it's because science is making English. It's made every paper in the biggest magazines have to be written in English. So it's very important. It's the language, really the language of science. Well, okay.
Well, it's a long story, so I'm gonna be quick, cut to the chase. So I started learning English just like him through computers, video games, and I used to read even though did not understand because well, RPGs you have to read, and then I used to pretend I was getting the message. And then when I got to college, before I got to college, I met some exchange students where I did my last my senior year, high school, and then I started hanging out with some Americans and people from other nationalities or other countries, and then I got to college and I met Cândido, and Cândido was one of my coaches, something like that. And then I did a course with Cândido. I went to the United States, and then I improved my English there, basically. But you have to like it. So read a lot and listen to music, right? Watch movies too. I watch a lot of things.
I want to thank Cândido to invite me to stay here, all the teachers, I forgot. Well, I started studying English with music. I love music in English, so I started when I was a child to translate music in English, schools of English, then as a teenager in YMCA when I met Cândido, Marcelo, and we went to USA, and then movies. In college, I needed to read a lot of stuff in English because law, when you have research in technology and this kind of stuff, you need to have English in your life. I wrote this book. It's about telecommuting. In this book, I need to have to do a large research in English. So I couldn't write this without English. And then I went abroad again in Congress. I needed to talk about my research in English. And some places like Havana, I went to Havana last year, and this year I could speaking Spanish, but when you're talking to another people, I can't speak Spanish, so let's do it in English. So I can communicate in English because I don't know how to speak Spanish. So if you go everywhere, you can talk in English, you can communicate, you can do everything you want. You have to learn English. And to do master's, PhD, you need to do tests, and you have to have English, because you can't get in a master's or a PhD without English. So that's it.
So, does anybody have questions about either about English or about their presentation?
You want to use the microphone? Sorry. Come on, guys. Abel has a beautiful English.
Oh, of course. I want to thank you to came here and speak for us. And I would like to know a little bit more about big data. You couldn't talk about it because of time, of course. And I would like to ask you about how big data can decide a presidential election race. For example, like had happened in US and probably has been happened here in Brazil in our presidential election race. So, and what can we do about it to not became a technology slave? Because now we see that the social networks is much more powerful than our speeches, for example. And what do you think about it?
That's a very complex one. But what I can say is in a quick way. For example, Cambridge Analytica in 2016 had a huge relevance on Trump's campaign due to data access from Facebook users. When you assign to a social media, you give them the power to control data, all the data that you access, all the personal data you have there. And then these companies, they get information from these social medias. Through they purchase, they buy it, and they use it in a way they can reach people, knowing what they consume in social media. So, and then there's a pattern they identify, and then give you the information they want. So you kind of live in a bubble. So we have to be very careful because there's a lot of fake news. But Facebook is fighting that now. I don't know if you guys know, but Facebook has a tool now that when there's something fake or somebody has pointed that as fake, Facebook points you to the real to the page that has the real information. So that's a real big problem that we're living now. And we have to be careful because fake news all over. WhatsApp is very it's a big problem because there's no control. I know WhatsApp is investing a lot of money in researchers to fight fake news. But big data is real complex because everybody in here has data, digital data, in social media. So very complex, very difficult to say what we should do in a matter to not give all that data to those companies.
Nice. I have a question?
Yeah.
Yes. I don't know what to do because we are out of time. Can you ask the questions directly to them afterwards, just because of time? I'm so sorry because it's already 12:30. We have to finish it, but I think you can ask them questions. It's not a problem, right? Directly. So I'd like to thank you very much. You mean English, of course. So Thalita, Marcela, and Gustavo for such interesting talks, and I think there was a lot of interesting knowledge shared here today. Thank you for accepting the challenge of presenting in English. I know it's not as comfortable as presenting in Portuguese. Most of the students, they're hungry, so they have to leave. Thank you for the strong students who stayed until the end. And I hope this was an interesting event for you here at Semana CET. And Semana CET continues in the afternoon. We have more things in the afternoon. Cassiano, would you like to talk to them? No, we're good? All right. So if you guys want to talk to them directly, you can do it now, and we're done for now. Thank you very much.